Okay. Our next speaker is Patrias, who will be talking to us on web invariants for non-crossing partitions.
Yeah, thank you. Thank you for coming, and thank you to the organizers. This is work with Oliver Pechenik and Jessica Stryker. What I want to do first is tell you how we came to the question that we ended up answering. So what was our motivation here? All right, so there's a well-known bijection between two-row standard Young tableau and non-crossing matchings, like we see it here. And in this bijection, if I do promotion on my tableau, that's going to correspond to rotation of my matching. If I do evacuation on my tableau, that's going to correspond to some reflection of my matching. And we have a similar thing with 3 rows. So there's a bijection between 3-row standard Young tableau and these objects called SL3 webs. And we have the same properties. So promotion on the tableau corresponds to a rotation of my web, and evacuation on the tableau corresponds to reflection of my web. So what we want to do is change this object over here. So instead of looking at standard Young tableau, we want to look at increasing tableau. So an increasing tableau is strictly increasing in rows and columns. So we have 2 examples here on this slide. These are a K-theoretic analog of standard Young tableau. So they're going to show up when we're looking at K-theory of the Grassmannian as opposed to cohomology of the Grassmannian. We have a lot of the same combinatorics. So we have a K promotion on these tableau and a K evacuation on these tableau. So what we want to do is mimic that same story with standard Young tableau. In 2 rows, things are looking pretty good. So there's a bijection between packed 2-row increasing tableau. So packed just means, for example, here I have every number between 1 and 10. So I'm not missing any entries. And again, if we do this K promotion on our tableau, that's going to correspond to rotation of our non-crossing partition. And if I do evacuation of my tableau, it's going to correspond to a reflection of my non-crossing partition. So that's pretty good. But we're going to run into issues when we move to 3 rows. And the issue is that we don't have an object to biject with. So we have these 3-row increasing tableau. We want some kind of object on this right-hand side to give us a bijection. And one of the motivations for this is, of course, we want promotion on the left to correspond to a rotation on the right, which is going to give us information about the order of promotion on these 3-row increasing tableaus. So that's kind of where we're coming from. This is the question we originally wanted to answer was, well, what kind of object can we make on the right here to give us this nice bijection that's going to work nicely with promotion? So we thought about this for a while and kind of just kept circling around and not getting what we needed. So we thought, let's just take a step back. And maybe we can fill in some other information that will help us. So our idea is, I didn't tell you all of the story with the standard Young tableau. So those objects on the right-hand side, the matchings and the SL3 webs, have some nice polynomials associated to them. And that's not true in our increasing tableau story. So maybe what we need to do is find some polynomials associated to those non-crossing partitions. Kind of fill in that part of the story with the 2-row increasing tableau, and maybe that will somehow give us enough information that we can guess what this object is supposed to be on the right-hand side here. So that's the question we're going to talk about today, and I'm going to start by telling you what those polynomials are for the standard Young tableau case. So we're going to talk about the polynomials associated to the matchings. All right, so to start, we have this matrix of indeterminants, and we're looking at polynomials in these variables. So for example, I have this polynomial P13, x1y3 minus x3y1, so just any polynomials in our variable set here. And we're going to have a left action of SL2. So I can take any element of SL2, multiply that by my matrix on the left. Of course, I'll get a new matrix. And in my polynomial, I'm going to replace my variable by the corresponding thing. So here, any place I had an x1, I'm going to replace it with an x1 plus 2y1 as we see in my example. And in this particular case, if I simplify that down, I get back the same polynomial that I started with, and this is going to be true for any element of SL2 with this particular polynomial. So we'd say that this polynomial is invariant under this action. We might want to ask which polynomials are invariant under this action. And classical invariant theory will answer that question for us and tell us that the set of the space of invariant polynomials is generated by the 2x2 minors. So this P13 we were looking at is, of course, the 2x2 minor using columns 1 and 3 in our matrix. And in general, we can specify any 2x2 minor by a Pij telling us which two columns we're using in our minor. So since these are generators for our space, we might want to think about products of our generators. And we're going to have two nice ways to encode the products of our generators. So here I have an example, a product of generators. I'm reminding you that the generators are minors, so that's our second line here. And one way we can encode these generators is by a diagram like we see at the bottom. So I have, for example, a P12 in my product. So I'm going to have an arc between 1 and 2. I have two instances of P34, so I have two arcs between 3 and 4. Pretty straightforward way to encode our product. We could do it instead using a tableau. So I have the same product of P's on this slide. Here, again, I have a P12, so I'm going to have a column in my tableau of 1, 2. I have two instances of P34. So I have two columns of 3 and 4. I can force my tableau to be weakly increasing in the first row, but then of course I don't get to control what happens in the second row. So I have kind of wild down there, but I have some tableau with weakly increasing first row. All right, so a little review on this slide. So our invariant space is generated by our 2x2 minors. If I have an M-fold product of 2x2 minors, I can encode that using a tableau of shape MM with weakly increasing first row, and just whatever the second row does is what it does. So from there, standard monomial theory is going to tell me that if I just look at semi-standard tableau, this is giving me a linear basis for the degree 2m homogeneous part of my invariant space. So again, the semi-standard tableau are giving me a basis. Right, so let's restrict our space a bit and only think about products where I'm using each index, each column of my matrix exactly once. So here I'm using each column 1 through 14 exactly once in my product. If I restrict to this space, then what do my two objects look like? Well, over here, I have tableau where now each entry is used exactly once. I have a strictly increasing first row, and of course, an uncontrollable second row. And my diagram now is going to be a matching since I'm using each index exactly once. It's going to be potentially crossing. This example is non-crossing, but a potentially crossing matching. So that's the two kinds of objects I'm getting if I restrict to using each column of my matrix of variables exactly once. So what happens then if I want to think about a basis in this restricted space? Well, then my basis consists of the set of standard Young tableau of shape MM and a set of non-crossing matchings. So for example, we can look at if n is 4, I'm looking at two-fold products. I have 3 of those, which I see in the first line, corresponding to these 3 tableau I see in my second line. If I want to think about the basis, I'm looking for the standard Young tableau. So I see that the first guy is in my basis, the second one is in my basis, and the third one is not. And then on the third line, I have the matchings. I can see the first element is a basis element because it's non-crossing. The second one is not, and the third one is. So one thing we can see from this example is that my two bases, my standard Young tableau and my matching basis, are actually distinct bases. They're giving us different polynomials that they correspond to. So since in this third example, in this third line down here, we have this crossing matching that's not a basis element, of course, we should be able to expand it in terms of basis elements, which not at all surprisingly, we can do with a crossing rule. So if I have any kind of crossing in my picture, I can replace it with the sum of these two non-crossing pictures. Probably very familiar to a lot of you. And we have one more piece here. We're going to have an SN action acting on the right. So I can take my matrix of variables and multiply on the right by an element of Sn, and that's going to permute the columns in my matrix. So we have an example of that here. So what's going to happen to my P13? I'm going to replace all the X1s with Xn's, etc. And I'm going to get some other polynomial. So now we have an Sn action. We've turned our space into an Sn module, which actually turns out to be the Specht module SMM. So kind of putting it all together, we have the Specht module and we have two bases for it, the basis of non-crossing matchings and the basis of standard Young tableau. We have a similar story in 3 rows. We'll skip the details, but all the stuff proceeds the same way. So if I'm looking at 3-row case, I'm going to have 3 rows of variables. We're looking at an SL3 action on the left and thinking about the invariant polynomials. That's a set of 3 by 3 minors, all the same story. Let's restrict to using each column in our matrix exactly once, and our bases are going to look like 3-row standard Young tableau and the SL3 webs. And again, these are then bases of the Specht module SMMM. So the same story in 3 rows. We're kind of focusing on 2 rows here, so we'll just skip those details. All right, so that's the background that we want to fill in for our story. So again, kind of the take-home point from that is if I have any kind of matching, I can easily associate a polynomial. So I'm just going to look at my matching. I see I have 1 and 6 match, so I'm going to have P16 as one of the factors in my polynomial. So I have some nice polynomial associated to my matching that's meaningful and invariant under some action. And this is what we want to recreate for partitions with no singletons. All right, so what do we want? So again, we want to be able to associate a polynomial to any partition with no singleton blocks, so no blocks of size 1. We want a nice SN action on this. So in particular, we want the long cycle to rotate our non-crossing partition. We also want to agree with some previous work of Brendan Rhoades. So Brendan kind of explored this just diagrammatically, not looking at polynomials, just looking at pictures. This is not an equality. And he has these crossing rules that he found. So we want our world to agree with his crossing rules up to sign. So that's kind of our wish list. Let's zoom in on these crossing rules just to notice a couple of things about them. So I want us to notice that the block size changes. Not everything inside of one of our crossing rules has the same block sizes. So let's look at, again, this is a minus sign, not an equality. Let's look at our third rule down here and let's take each of our vertices literally. So this is A1, A2, A3, B1, B2, B3. And let's look at the block sizes. So in this left-hand guy, I have 2 blocks of size 4. Then I have blocks of size 4, and now I have a block of size 6 and size 2, 5 and 3, 5 and 3. So this is going to be important in our next slide. We see that the block sizes change in our crossing rules, but the number of blocks does not change. So in each of these rules, everything has 2 blocks. We're not going to gain or lose blocks with our crossing rules. Okay, so let's say we're trying to make our polynomials associated to our partitions, and we just want to make a naive guess. So I would claim the most naive thing you could do is just try and directly imitate what we just did. So I have a partition here. I see I have a block composed of 1, 4. So let me take a minor P14. I'm going to take all top justified minors. So I'm using columns 1 and 4 in the first 2 rows. I see I have a block 2, 3, 6, 10. So let me take P 2, 3, 6, 10, where again, I'm using columns 2, 3, 6, 10, and the top 4 rows of my matrix M over here. And then I have my block 5, 7, 8, 9. So I'll take P 5, 7, 8, 9 and look at that product of minors, which is kind of just trying to copy and paste exactly what we did with those matchings. But this is not going to work. And we can see that by looking again at these crossings rules that we're trying to keep true. So notice here I have, let's see, I'm now drawing over myself many times, but I have 2 blocks of size 4 that are crossing each other, the red and green block. So I'll kind of go back to that in the crossing rules. But first, let's notice in my polynomial that I currently have, I'm only using the first 4 rows of variables. So I can really cut this matrix off at x4, 1, x4, 10. So this only uses the first 4 rows of variables. And again, I have these 2 blocks of size 4 that are crossing. So I should be able to use Brendan's crossing rules and uncross those using, again, the 3rd line of our crossing rules. But notice if I do that, I started out with 2 blocks of size 4. I'm going to end up on the right with a block of size 6. And this term is going to use 6 rows of my variables. So we see a problem. We can't have just 4 rows of variables on the left and 6 rows of variables on the right. So I can see that my naive guess of just take upper justified minors corresponding to the blocks is not going to be what we need to do. So we're going to need to be a little more creative than that. And let me show you what we ended up with here. So I'm going to start again with a partition with no singleton blocks. And I want to then create a set of what we call jellyfish tableau. So you can see the set of jellyfish tableau below. Our rules are as follows. So the blocks of my partition are going to be the columns of my tableau. So I have block 1, 4. So each jellyfish tableau has column 1, 4. I have block 2, 3, 6, 10. So I have a column with 2, 3, 6, 10. And I have block 5, 7, 8, 9. So I have a column with 5, 7, 8, 9. Each column is going to have an entry in the first 2 rows. So our first 2 rows are crowded. They're kind of solid up top. And then below that, there's exactly 1 entry in each row. So that's why we're calling this is our jellyfish, because it's supposed to look like a jellyfish. So it's kind of solid on the top, and then it has some kind of tentacles dangling down. So we're going to form that tableau in every way possible. And we see all of those examples here. And each of these jellyfish tableau is going to be corresponding to a product of minors. So let me show you one example of that. So let's take our jellyfish tableau here. Each column is going to correspond to a minor, but we're just going to be creative about which rows of our matrix M we're going to use in our minor. So let's start on the left. So I have this column 2, 3, 6, 10. So that's going to correspond to a minor that uses columns 2, 3, 6, 10. So these are the columns. And the rows that I'm going to use for my minor, 2, 3, 6, 10. The rows I'm going to use for my minor are determined by the rows that my column uses. So my first column here uses rows 1, 2, 3, and 4 in my tableau. So I'm going to use rows 1, 2, 3, and 4. So that's my first minor corresponding to my first column. For my next column, I'm using columns of my matrix M 5, 7, 8, 9. And for the rows of my minor, I'm going to look at which rows are used in that column of my jellyfish tableau. And I see that I'm using rows 1, 2. Whoops. Come back. I'm using rows 1, 2, 5, and 6. And lastly, I have my column 1, 4 in my jellyfish tableau. So this is going to be the minor where I use columns 1 and 4. And my entries are in row 1 and 2. So I'll use rows 1 and 2 in my minor. I also have a sign out front. We have some inversion number. Let's call this T. That's defined how you would guess it would be. So our jellyfish tableau is going to correspond to some sign and then the product of these 3 minors. So what's true about these jellyfish tableau then is that the number of rows that we're using in our polynomial doesn't depend on the block size, it just depends on the number of blocks. So we said that that was okay with those crossing rules that we were trying to keep.
Take about 2 more minutes.
Yep, perfect. So again, if we have our non-crossing partition or our crossing partition in this case, we're going to form our set of jellyfish tableau and then sum up all the corresponding polynomials for each of those. And that is our polynomial that we're looking for. All right, so our main theorem then is that if we take the non-crossing partitions, they're going to give us a basis. So the non-crossing partitions of 2D plus L into D parts with no singletons is a basis for the Specht module SDD 1 to the L. So let me just pause there for a second. So the Specht module shape is just what we get if we kind of shake out all the jellyfish and left justify everything. So in this case, we'd be looking at, we're just smushing everything to the left, and that's the Specht module that we're talking about. So our non-crossing partitions give a basis for the Specht module, and we have a nice action, a nice SN action. So the long cycle is going to rotate our partition, and W naught is going to reflect our partition. Okay, the crux of all of our arguments are our generalized crossing rules. So I'll just show you the picture of them. So these can specialize to Brendan's rules that we are trying to keep, but they're much more general for our purposes. And then lastly, I'm calling them invariant polynomials. What are invariants of what? So I have my matrix of indeterminants, and they're invariant. My polynomials in these variables are invariant under a left action of this subgroup of SLD. So I have a 2x2 block up here, a big block on the bottom, determinant 1. So they're invariant under that action there. And I think that's all that I have to say. So thank you. Me?
Yeah.
Yes.
Something went funny with the screen, but that might have been on our end. Are there any questions?
Thanks for the lovely talk, Becky. I was wondering, I remember in Brendan's paper, he has there's some tiny little comment where he says, you could do this other crossing rule or other uncrossing rule. I forget exactly how it works. So, I mean, can you say anything more about why Brendan's rule is exactly the right rule for you to be using?
Not anything very meaningful. It just seemed to work for him, and so we thought maybe it should work for us too. Yeah.
Okay, thanks.
So it seems that many of the tools you use are available also for other types. Have you thought of trying this?
We have not. No, we haven't thought about that at all. So I accidentally skipped my what are we going to do in the future slide. But yeah, we haven't thought about other types. We still want to go back to our 3-row increasing tableau question. That was our original motivation. We want to think more about what we can do with jellyfish tableau, and we want to connect this better to Brendan's work. But other than that, we haven't thought about anything. So we're still
in
just
particular, symplectic case would be natural candidate, right?
Yeah, we haven't thought about that at all.
Okay, thank you.
And is 3-row like the limit for this kind of thing, or do you think 4-row tableau would also be interesting?
So in the standard Young Tableau case, the webs get crazy after 3-row. So I think Jessica and Oliver and 2 other co-authors are working on the analog in the standard Young Tableau 4-row case. But in general, the web situation isn't what we want it to be in the standard Young Tableau 4-row case. And for the increasing tableau, the promotion gets crazy after 3 rows. So we wouldn't expect anything nice, maybe.
Right, right. Now it's interesting how increasing Tableau really help make things work in certain situations. So it's good that it does it here too. Yes, there's a question back there.
Do you know if you can translate this into a basis of the top cohomology of the corresponding Springer fiber?
I don't know that. Yeah, I don't know much about that at all. We've started working with Heather Russell to learn more about Springer fiber things, but personally, I don't really speak that language, so I can't say.
Anything else? Let's thank Becky again then.